Okay. Hello everyone. In this slides, I am going to explain you the JK flip-flop. Okay. As in the previous slides, we have discussed the SR flip-flop. So there were two indeterminate states. Okay. So to get rid of those indeterminate states, we have modified the SR flip-flop in the JK flip-flop. So this is the same as the SR flip-flop. As you can see, there are 4 NAND gates, a clock pulse, J and K are the inputs like the S and R, but the difference is you can see Qn bar is feedback to one of the input of the first NAND gate and Qn is feedback to one of the input of the second NAND gate. So basically this is the only difference. We have added the another inputs here as Qn and Qn bar. Okay. So why it is named as JK? As you can see here, because it is invented by John KLA, that is why it is named as. So it is named on the person who developed it. Okay. So now this is the characteristic table, this is the truth table, which I am going to discuss it in the last slide. And as we discussed in the SR flip-flop how to make the characteristic table, now I am going to discuss how to make this characteristic table. So as we discussed in the SR flip-flop, we have 3 inputs Qn, J and K. So if there are 3 inputs, then there will be 8 possible combinations. We have made the 8 possible combinations. And how we have determined the Qn plus 1? The same method as we did in the SR flip-flop, we will do in this JK flip-flop. Now as you can see, I will explain you in the next slide. I am going to take the 4 cases, case 1, case 2, case 3 and case 4. In the case 1, when J equals to 0 and K equals to 0. Okay, so here there are 2 cases, this one and this one, right? So we have to depict the output here. So this is the JK flip-flop diagram. As you can see, J is 0, K is 0, obviously the clock is always 1. Okay, and now we know if one of the input is 0 of the NAND gate, we get the output 1. If one of the input is 0, we get the output 1. Okay, and here we can see this Qn bar is here, Qn bar, and this Qn is here, this Qn. So we have to find this Qn plus 1. So here I have written here Qn plus 1 equals to 1 into Qn bar, 1 into Qn bar whole bar. Okay, so 1 into Qn bar means it will be Qn bar and Qn bar, and this is the whole bar. So if there is a double bar, that means it is getting cancelling each other, so we get the output Qn. And the same method we have find the Qn plus 1 bar, so we are getting Qn bar. Basically, what will be my next state? The next state will be the assumed output. Whatever we have assumed, it will be the assumed output. So we can see in the truth table, we can see in the characteristic table, we have assumed Qn equals to 0. So our next state will be 0. Okay, and we have assumed Qn equals to 1 here. So the next state will be 1. Okay, now the next case is when J equals to 0 and K equals to 1. Here, when J equals to 0 and K equals to 1. J equals to 0 and K equals to 1. Now it is the same NAND gate diagram of JK flip-flop. Here you can see if any of the input is 0, the output is 1. Okay, and now in this, here you can see K equals to 1, clock pulse is 1, but we don't know what is the third input. So the third input is basically the Qn. So I have written here Qn. Okay, so what will be the output here to the NAND gate? 1 into Qn whole bar. Okay, so the output will be Qn bar. Okay, is it clear to you? The output is Qn bar. Now here we can see so we can find out the Qn plus 1 bar. How can we find? On this NAND gate, we can see this is Qn which is getting feedback here. So this is Qn, this is Qn bar. So what will be the output? Qn into Qn bar whole bar. So Qn into Qn bar is 0. We know the property A into A bar equals to 0. So it is 0 and the bar is 1. Okay, so we are getting the value here. So if we get the value here, that means the complementary output will be 0. So this is 0. Okay, so basically Qn plus 1 equals to 0. So we can see, irrespective of the output assumed, the next state will always be 0. So as we can see, this is 0 here and this is 0 here. Okay, now we will talk about the case 3. As you can see, this is the case 3 when j equals to 1 and k equals to 0. J equals to 1 and k equals to 0. Now here we have again draw this J-K flip-flop diagram, and you can see j equals to 1, k equals to 0. Clock pulse, usually as usual it is high, 1 and 1. Now here from this NAND gate we can already get the output because one of the input is 0, so the output is 1 here. Okay, now in this one both the inputs are 1, so this input will be, as you can see here, this is Qn bar. Okay, so if it is Qn bar, so what will be the output? As you all know, because these are the inputs to the NAND gate, so the output will be 1 into Qn bar whole bar. So the output will be Qn. Okay, and now for this NAND gate, because we have to depict what is Qn plus 1, we have to depict this. So what is Qn plus 1? As you can see here on this NAND gate, what is the input? Another input is Qn bar. So what will be the output? Qn into Qn bar whole bar. As I have written here, Qn bar into Qn whole bar. So A into A bar is 0. So I have written 0 here, and this is a bar. So it is 1. Okay, so we are getting a value here, so we are stopping here, and obviously the complementary output will be 0. Okay, so as we can see here, we are getting 1 as the output as a next state. That means irrespective of the output assumed, irrespective of the previous output, we are getting 1 as the output. So here it is 1 and here it is 1. Okay, now the last case, which is a very interesting case, it is a toggling case basically. J equals to 1 and k equals to 1. Okay, in the SR flip-flop, this condition was invalid. That means if we are doing the SR flip-flop, that was basically the invalid state, or we can say it is the unused state. So one state was totally unused. But in j equals to 1 and k equals to 1, it is the modification of the SR flip-flop. So this is known as the toggling condition or the toggling state. Okay, now in this one, j equals to 1, as I have written here, j equals to 1, k equals to 1, clock pulse as usual, it is high, so 1 and 1. Now I will write the output. As you can see, this is Qn bar, which is going here, so it is Qn bar, and here it is Qn, which is going here, so it is Qn. Okay, now we will find the output. So what will be the output at this NAND gate? The output will be 1 into Qn bar whole bar. So it will be Qn. Okay, what will be the output here? 1 into Qn whole bar. So the output will be Qn bar to this NAND gate, and the feedback is here Qn bar and the feedback is here Qn. Now we can find the Qn plus 1 first. So it will be Qn into Qn bar, Qn into Qn bar whole bar. That means it is 0 bar. That means it is equal to 1. Qn plus 1, Qn plus 1 bar will be Qn into Qn bar, Qn into Qn bar whole bar. That means this is 0 complement output equals to 1. So basically the output are both 1. So this is the toggling condition. Now in JK flip-flop, because this is the feedback, these both transistors are the same transistors. So what basically we will get the output at one place, and that output will feed back to the another place, and then we will get the another output. Okay, so as you can see here, Qn plus 1, we will assume any of the outputs. Like I have assumed Qn bar to be 1 here, so this one is going 1 here. So what will be the output? Qn into 1 whole bar. So it is basically Qn bar. Okay, so whatever will be the output, whatever we have assumed the output, the next state is the complement of the previous state. That means if I have assumed the previous output is 0, then the next output will be the complementary output. That means it will be 1. So we can see in the characteristic table here, it is 0 and the next state output is 1. It is 1 here and the next state output is 0. That means it is the complemented output. Okay, so that means in JK flip-flop, for J equals to 0, K equals to 0, we getting the assumed output. When J equals to 0 and K equals to 1, we getting 0. When J equals to 1, K equals to 0, we getting 1. When J equals to 1, K equals to 1, it is known as the toggling condition, and this is basically the complementary of assumed output. In the next slide, we will see how to make this truth table. So in the truth table, you can just see it's just a normal truth table from the characteristic table. J and K is the 0 and 0. So here you can see 0 and 0 here. So when J equals to 0 and K equals to 0, what was the output? It was the assumed output. So that means it is Qn. When J equals to 0 and K equals to 1, what was the output? It is 0. When J equals to 1, K equals to 0, you can see when J equals to 1, K equals to 0, J equals to 1, K equals to 0. In both of the cases, we are getting the output 1. So I have written 1 here. When both of the inputs are 1, J equals to 1 and K equals to 1, you can see here what is the output. Basically, you can see it is the complementary output as we have discussed in the previous slide. So if it is 0, it will be 1. If it is 1, it will be 0. So basically I will write here Qn bar, the complementary of the previous output. So this is the truth table of the JK flip-flop. This is the characteristic table of the JK flip-flop. You have to remember these truth table, because when we will finish with the flip-flops, we will discuss the realization of the one flip-flop from the another flip-flop. So we will use this characteristic table and the truth table. Okay, so this is all about the explanation of the JK flip-flop. In my next presentation, I will show you the explanation of the master-slave flip-flop. Thank you so much.